Okay, thank you very much. I'd like to introduce myself, Mike Hopkins. I'm CEO of company IMPEDANS, and we make plasma measurement systems. Most of our customers are in industry, so we're interested in problems associated with industry. And today I wanted to talk about retarding field energy analyzers. Retarding field energy analyzers are multi-grid systems used to analyze ion energy distribution functions. So the energy of ions arriving at a surface. You want to measure the flux and the energy of ions arriving at a surface. But in some applications, knowing the one-dimensional energy is not sufficient. And people would like to know what is the angle of the ion arriving at the surface as well as the energy in the perpendicular direction. So the talk then, I want to introduce the idea of angle and how we intend to try and measure the angle of ions arriving at a surface. Introduce the concept of a variable aspect ratio, how you can have an aperture with a variable aspect ratio that can discriminate the angle of the ions arriving. And then how we can combine this concept of a variable aspect ratio with energy discrimination so that we can measure the energy of the ion in the perpendicular direction and we can measure the angle of the ion. And with those two, we then have the two-dimensional energy distribution of the ions. And then I'm just going to give an example of some recent measurements then with a system. So the idea behind this then is we're looking at an ion which is arriving at a surface. And we want to, first of all, we want to measure the energy of the ion. And so we're going to use multi-grid system to measure the energy of the ion. And so we put a retarding potential here, and that retarding potential will stop low energy ions and allow the high energy ions through. And then if we change that retarding potential, we can reduce the ion current to zero. And the derivative of the current with as a function of this grid gives us the ion energy distribution. But that's the energy of the ion perpendicular to the grids. That's this energy here, E perpendicular. Now, how do we measure this energy here, which is E parallel of the ion? And it turns out for some applications, that measurement is very important. If you're looking at, say, etch applications in the semiconductor industry, if ions are coming in at an angle, then they will etch at an angle. And that won't produce fast chips. So you scrap your product. So how do we measure both the perpendicular energy and the parallel energy of an ion with a standard gridded energy analyzer? Well, the one way to do it, and this way is well known, is to change the aperture ratio of two gridded systems. So you can have a long aperture here, then an ion coming in at a particular angle will only get through if it has a certain angle. And then if we have a shorter distance here, then an ion coming through will get through with a larger angle. So in this case, if both of those are the same angle, then this ion doesn't get through because it hits this aperture, whereas this ion gets through. So you can imagine if we could vary the aperture, we could look at the angle of the ions coming through. But there's a simpler way of doing it. If instead of varying the aperture, if we have an energy analyzer with a fixed aperture, so we just fix L and we don't change L, but instead we apply a voltage between the two apertures, which creates an E field, then if we have zero field here, then the ion has a certain angle. But if we now apply a voltage between these two apertures, we increase this perpendicular energy of the ion, and the ion now gets through. So we're changing the effective aspect ratio of the two apertures by changing the voltage. So how will this work in practice with a gridded energy analyzer? So we have an ion coming in here with its two component energies, And we apply to this grid and to this grid a retarding potential, which is used to measure the energy of the ions. So as we increase this retarding potential, ions are stopped. And then we can consider the grids as one grid. And then if we also apply as well a voltage between grid 2 and grid 3, which we'll call V angle, then we can change the retarding potential, and we can change V angle as well. And now everything then is collected. The ions are collected on the collector, and we measure the current. So the theory then behind what we want to do is we have a standard retarding field energy analyzer. It's designed to have an electric field in the x direction only. And so it's a planar system with all grids parallel to each other. So in principle, it only measures the energy perpendicular to the surface. The discriminator potential is at G2, is used to separate ions with different energies, and acts only in the E perpendicular component. So we bias grid 2 relative to the entrance at a voltage which discriminates the ion energy. The E parallel component of the energy is unaffected by the electric fields inside the sensor. So as we change the voltages between the grids, the perpendicular energy is changed, but the parallel energy is not changed. So at any location inside the sensor, the E parallel component of the ion energy is identical to the E parallel energy of the ion entering the sensor. So now by varying the angle voltage between grid 2 and grid 3, the acceptance angle for which the sensor is valid can be changed dynamically. So that's basically the idea behind it. We have a picture here sort of showing how it might work. So you have an ion, say, entering the sensor with a particular angle alpha, the E perpendicular, E parallel and E perpendicular. As we approach grid 2, which is the discriminating grid for energy, we slow the ion down till it's almost stopped, and we see that its perpendicular energy is tending towards 0, and its parallel energy remains the same as what it had when it entered. And now, as we pass through grid 2, we apply a voltage between grid 2 and grid 3, which we call the angle voltage, and that voltage then now accelerates the ion in this direction. It leaves this energy unchanged, and so now we can change the angle between these two grids. And this angle will determine whether the ion gets through the apertures or not. So if this angle voltage is 0, the ion will not get through the apertures. If this angle voltage is very high, the ions will get through the apertures. Now, whether they get through or not is just determined by the geometry. If the ion will reach the collector only if tan alpha is less than 2a over L, where a is the radius of the aperture and L is the distance between the two apertures. That's simple geometry. And tan alpha is equal to tan beta, where tan beta is the angle entering the sensor, multiplied by 1 over r, where r is the ratio between the retarding potential and the angle potential. So here's what it sort of looks like in terms of a picture. This energy parallel doesn't change, but if we set, say, a low voltage angle voltage, then the ion comes through with this angle. If we increase the angle voltage, the ion comes through with this angle. If we increase the angle voltage more, the ion comes through with this angle, and cetera, as we increase the angle voltage. And if we look at then the current that gets through to the collector, in this case, with, say, a 45-degree acceptance angle, no ions get through at this point here. And so the current to the collector is 0. As we increase the angle voltage, then ions start to get through, and we get a small current at the collector. And then as we increase the angle voltage more and more ions get through to the collector. And if we take a derivative of the current collected as a function of angle voltage, we see a peak here, and that peak corresponds to the original angle of the ions coming into the detector. And so basically, we have a way of measuring both the energy perpendicular and the energy parallel. So the discrimination grid G1 then selects the energy window for an ion for detection. At each energy selected, the potential difference between the G2 and G3 is swept through the various ion angles, and the current is collected at each set of angles. The current derivative shows the angle distribution. So the derivative of the current on the collector with respect to G2 is the ion energy, and the derivative with respect to the difference between G2 and G3 is the angle distribution. So what does that actually look like for ions accelerated to a surface? So this is a capacitively coupled parallel plate discharge. It's 13 megahertz. It's run at about 10 millitorr, and the gas we're looking at is argon. Ions are accelerated to the bottom plate with an energy of around 20 to 25 eV. And if we now vary the voltage on grid 2 and get the derivative of the current, we see the ion energy distribution function, which is the blue one. But that's determined for angles between 0 and 3 degrees. So the blue curve is ions arriving at the surface with angles between 0 and 3 degrees. This curve here is ions arriving at the surface between 3 and 6 degrees. And then the next one, the grey one, is ions arriving between 6 and 9 degrees. And we can see that basically the vast majority, 98% of the ions, are arriving at the surface perpendicular to the surface. But we have a small component of ions arriving between 3 and 6 degrees. And this can be critical in certain applications. As I mentioned, etch applications would be an example. And we can see that there are no ions really arriving at higher angles. So basically, we have found a way to take a standard retarding field energy analyzer, which is a planar device, and by using apertures and a bias between the apertures, we've been able to angle resolve the ion energy distribution arriving at the collector. And we can look at an average over, say, 10 eV, the most important ions in that bunch, and we can see that, as I said, 90% of the ions are arriving at a 0 angle, but we have a small component arriving at 6 degrees and then essentially going to 0 at higher angles. So then to summarize, angle is determined by the ratio of E perpendicular to E parallel of the ions entering the analyzer. The collected current is reduced when for high angles when the ion crosses through the aperture. And by varying the aspect ratio of the aperture, we can change the collected current. But we do that by putting a bias between the apertures. So this is we call V angle. The collected current becomes a function of V angle. And by taking the derivative of the current with respect to V angle, we get the angular distribution of ions arriving at the collector. So thank you very much.
Sheath formation between your retarding spectrometer and the plasma, and you have a grid with some finite dimensions. So the potential lines could be curved, how it could influence on measurements of the real, let's say, real actual distribution of ions versus.
Okay. So if you have a perturbation of the surface, then you want to keep that perturbation of the order or less than the Debye length of the plasma. So the grids we use have a 20 micron spacing. And for this plasma, the Debye length is maybe 50 to 100 microns.
What is the sheath width?
What is the sheath width? The sheath width would be about a millimeter, half a millimeter to a millimeter, depending on the voltage on the bottom plate. So the sheath width is quite large relative to the Debye length, and the Debye length is large relative to the grid spacing.
So you will have some electrical penetration inside.
You will, but that usually depends on the ratio of the distance between the grids and the grid spacing, the grid width. So the grid's aperture is 20 microns, and the spacing is about 200 microns, and that will give you about a 1% saddle in between the grid spacings. So that can be calculated fairly easy. We have looked for scattering on the grids, and we've looked at aligning the grids and randomizing the grids. If we align the grids, we see some structure, and we think it's due to interference because of scattering. If we randomize the grids, we see no effect. So we think that just by randomizing the grids, you remove any scattering, because a typical ion trajectory does not go through the same hole, it goes through a different hole on the grid. And so by randomizing the grids, you remove any effects. That's what we've found by experience.
In the implementation of this method in the hardware, how long does it take to do all the sweeps from 2 dimensions and to process the data?
Very good question. A typical sweep with a single energy sweep can be as quick as 10 or 20 milliseconds, but typically it's of the order of a fraction of a second. If you wanted to do up 0 to 45 degrees, that's about 15 or so angles, then you have to have 15 voltages on top of that. So that's about 15 times as long. And so practically that's somewhere between a few seconds and 15 to 20 seconds. That sort of time frame. So it's longer, but it's not impractical.
National Linear Collider, there's a big problem of it's called electron cloud.
Yeah.
Which is generated in the vacuum.
Yeah.
And the problem is to characterize this plasma.
Yeah.
And one of the problems is that you have also recessed electrodes to collect these electrons and measure them and so on. One of the problems is that once you have an electron impinging upon whatever electrode you have, it may generate other electrons. So how you avoid here, talking about ions of 30 or so MeV, the electron volt, how you avoid generation of other electrons and...
Okay, so... Yeah, we've 2 issues. The first issue is secondary electrons created by ion impact on the surface. And we do get secondary electron emission. I didn't show it here, but we often include a 4th grid to prevent secondary electrons emitted from the collector leaving the collector. So we bias that grid to push electrons back onto the collector. The issue of those electrons causing a problem inside the sensor, we're operating on the left-hand side of the Paschen curve, and so the electrons get collected by a surface before they've interacted with the gas or caused any further issue.
So they jump from one electrode to another in your configuration.
Yeah.
Then effectively it's like an ion moving in the opposite direction.
Yeah, and so the only surface that we're concerned about then is the collector. And so we put a grid above the collector, and we bias that grid more negatively than the collector in order to repel back electrons that come from the collector. So we can suppress completely secondary electron emission from the collector. We can't suppress it from the other grids, but we can from the collector, and the collector is the one that's important. So we find in low energy applications where you're up to 100 EV or 200 EV, you can get away without suppressing those electrons. It adds about 20 to 30% to the current and depends on the gas. But at high energies, 500 EV to several thousand EV, the secondary electron emission can exceed the ion current, and so you have to use a 4th grid to suppress secondary electrons.
Okay, thank you again.